Welcome to Chapter 5 of College Algebra. My name is Gregory Carlson, and in the sections leading up to this, we've been looking at how to solve all sorts of equations. In Chapter 3, we learned how to use synthetic division to solve all types of polynomials. In Chapter 4, we learned about exponential and logarithmic functions, and that enabled us to solve x when it was in an exponent. But that leaves out a whole branch of different types of problems which are called systems of equations, or you'll sometimes hear them called simultaneous equations, meaning that you have two different equations that are existing in the same space, in the same plane, or whatever your space is, and you want to find solutions that satisfy all the equations all at the same time. It sounds hard, and there will be a few hard problems in this section, but eventually we're going to learn how to use a matrix to solve basically any system of equations that you want, and how a computer uses a matrix to solve a system of 100 equations and can find a solution to all 100 of them. So I hope you will take the red pill and join me as we go along and figure out how to do this. So let's start with simple 2x2 systems, which are sometimes not so simple, but we'll start with 2x2 systems. And there's three kinds of things that can happen when you solve a system like this. The first thing that can happen is you get a system that's consistent and independent. Okay, and what that looks like is when you have a graph, there's the line that represents all of the solutions to the first equation. And here's a line that represents all of the solutions to the second equation. And we see that we get 1 point, that's the solution. So you would write that as the solution is 1, 3. Or you can write x equals 1 and y equals 3. And this point right here would represent the point to 1, 3. So that's the first thing that can happen is you get one system of equations. And when you're solving it, that means you're going to get x equals a number and y equals a number. And this happens most of the time. Most of the time we get one solution where the two lines cross in only one place. The second thing that can happen is you get inconsistent, but the lines are still independent. So let's look at an example of that. Two lines that are independent are still two different lines. However, if we get a situation like this, where these two lines are parallel, those little arrows that I just drew on mean that they're parallel lines. If these two lines are parallel, that means they're never going to cross, which means that we're not going to have a solution. And that's why it's inconsistent. Inconsistent means no solution. When you're solving an equation, and you get something crazy like 1 equals 0 or -3 equals +3, if you get something like that, you know you've got a system that's inconsistent. There's no value of x or y that can make 1 equal 0, and so therefore there's no solution. And we'll look at examples of all of these as we go on. Finally, there's consistent and dependent. So let's take a look at what these mean. So in this kind of situation, we have one line, and we find that the other line is just a scalar multiple of the first line. In other words, one equation will just reduce into the other one. And so essentially what you have are two lines that are on top of each other. So that's why I made this line a little bit bolder. When you're solving it, you get something like 0 equals 0, or 10 equals 10. Now you notice it's kind of similar to what we had with the inconsistent and independent, but this time the statement's always true. And so in other words, it doesn't matter what x and y are, the statement is always true. So on this one you have one solution. If it's inconsistent and independent, you have no solution. Or on the third case, we have infinite solutions. And another way of saying that is all real numbers. Okay, so those are the three categories that we're going to run into as we're doing this. Either one solution, no solution, or infinite solutions. So let's really understand we know what consistent versus independent versus dependent versus inconsistent means. You can see that we're consistent if we have a solution. Here we had infinite solutions, here we had one solution, but both times we at least had a solution, so that's what made it consistent. It was inconsistent when it was no solution. So then what's the difference between independent and dependent? Well, independent means the lines have their own identity. They're unique lines. Dependent was the same line on top of itself. You couldn't differentiate between the two lines. So consistent versus inconsistent means, do we have a solution? And independent versus dependent means, are the lines distinct? This is important because when you solve a problem, you'll get the answer, but you'll also need to know which category applies to it. So that's why I started this section with this. You need to know what these words mean so that when you solve it, you can say what category it is. So I think we have enough time to go ahead and look at the first example. So let's do that. This hopefully is some review for you. The first method of solving a system of two equations is the method of substitution. So you can see here we have two equations and two variables, so we should be able to come up with some kind of answer. So when do you know to use substitution? You know to use substitution when you have a variable that's isolated, or you have a variable that's really easy to isolate, okay? So we see that we have x equals 5y minus 4. In other words, x is another name for 5y minus 4. These two quantities are equal. And so because these two quantities are equal, because this is the same quantity as x, I can take this quantity and replace x in the other equation. So all I did there is just draw a little arrow. So we can take this quantity and replace x in the other equation because x is equal to 5y minus 4. Okay, so let's solve this really quickly. I believe that's just a stray mark. It was. So the second equation can be rewritten 4 times 5y minus 4 minus 3y is equal to negative 33. So in other words, the entire equation stayed the same, except we replaced x with 5y minus 4. And now you have one equation with one variable, and so now we can solve. Do the distributive property. 20y minus 16 minus 3y equals negative 33. Combine like terms. Hopefully this part's easy for you after doing it so much. So we get 17y minus 16 is negative 33. Add 16, add 16. Oops, that cancels. 17y equals negative 33 plus 16, which is 17, but the negative's bigger, so it's going to be negative 17. And divide by 17, divide by 17, we get y equals negative 1. So we found our y value, and we've done most of the work we had to do. So y equals negative 1. Now what's nice is we can go back and plug it into either equation, and we'll get the answer. So let's pick this equation since it's already solved for x. So x is equal to 5 times, now we substitute negative 1 in for y. So see how this equation is the same as the top equation, except I've replaced y with negative 1. That gives me negative 5 minus 4, so x equals negative 9. All right, so we have, that's the answer. And you can rewrite this as negative 9, negative 1. So it might be the best to show the answer as a coordinates, negative 9, negative 1, but it's okay to say x equals negative 9, y equals negative 1. So which of the three categories is this problem? 1, 2, or 3? We have one solution, and we were able to get x and y equals, so that means this system is consistent and independent. Easy as that. Let me show you one trap you can fall in. okay? It's really important that when you're substituting a variable into another equation, you never substitute the same thing into itself. If you substitute the same thing into itself, it creates a circular argument and you get infinite solutions every time. So don't make that mistake. Never take 5y minus 4 and put it over here to replace that x, because then you get the same thing equals itself. Another thing to watch out for is, do you see when I plugged in this in for x? I had to put parentheses around it because this was 4 times x. And since x is all of this amount right here, I need to do 4 times the entire amount, which is why it needed to go into parentheses. We've done our first example. In the next video, we'll do example number 2. See you there.